say you hate me. I don't believe.
We've already seen how magnetic field exerts a force on a conductor that carries current. So it comes not as a surprise that there's also going to be force to charges that are moving in the magnetic field by themselves without being confined into a conductor. The mathematical treatment of this situation is very similar. So the force vector is given by charge q. So this can be either negative or positive depending on the particle, multiplied by cross product of a velocity of the particle and the magnetic field. On this example here on the right, we have a magnetic field going into the page, as shown by these blue crosses. And then we have an electron, so a negative charge that has initially velocity to the right. So now we would like to investigate what happens. So first we have to define the direction of the force. So to do that, we need to calculate V cross B. So we point our fingers towards V, which is to the right, and then we have to curl our fingers towards B, which is into the screen. And in this case, our thumb ends up pointing upwards. But because the charge of an electron is negative, the force will be in opposite direction, in this case, downwards. Therefore, as the electron continues with the velocity to the right, it also experiences force that tries to curve its path downwards. And so we have this down curving trajectory. And if we evaluate the force again a little bit further at point Q, we see that the direction of the force changes along the trajectory, and it's always pointed perpendicular to the velocity. So in effect, it ends up into a circular trajectory, traveling in clockwise direction in this case. We can analyze the physics of this one a little bit more in detail. So there's a force acting towards the center. So that hints us that it's going to be centripetal acceleration what this electron experiences. So using Newton's second law, the sum of forces equals mass times acceleration. The force in this case is the magnitude of F, which is Q times V times B times the angle between the velocity vector and the magnetic field vector, which is always 90 in this case. The velocity is on the plane and the magnetic field is straight into the plane. So the magnitude of the force is Q times V times B. And because it's a circular trajectory, the acceleration is V squared over R. You might remember this from previous physics. That V cancels with that one, so we can solve for the radius of this circle. So R is m times V divided by Q times B. Now let's see what happens if instead of an electron we have a proton in this field, and it also has initial velocity to the right. So according to the right hand rule, we cross V and B, and our thumbs ends up pointing up. And because the charge of proton is positive, that is in fact the actual direction of the force. So the proton ends up also on a circular trajectory, but its radius is going to be much larger, because according to this formula we see that heavier particles, for them the the radius is much larger. So this technique in fact can be used for sorting different kind of elements or particles that have electric charge. You can sort them based on their mass, velocity, or charge, or some combination of these. The peculiar thing about charges in magnetic fields is that the magnetic field can only alter the trajectory of the charge if the charge is moving, so only if it has some velocity. And then when it's under the influence of the magnetic field is not able to change its velocity. It only can change its direction. So for example, magnetic fields cannot be used for stopping particles, only for guiding them. For stopping them, we need electric fields. In fact, the complete picture for a charge moving in both an electric and a magnetic field would be summing the two forces. So first of all, the electric force Q times E plus the magnetic force Q times V cross B, which can be grouped into E plus V cross B. A good example of this equation in action is a cathode ray tube, or CRT. Cathode rays, they are same things as electrons. For historical reasons, before electron was discovered, they were called some mysterious cathode rays. So anyway, so here we have a cathode ray tube, and how it works that we have some electron source here. It's usually by heating this piece of metal, some electrons are ejected. And because they are negatively charged, they will be attracted to this high potential, high voltage, positive voltage here on this plate. And the plate has a slit, so some of the electrons can go through. They have high velocity by this point. And then they come into this section where we have electric field plates that will deflect the electrons according to this force Q times E, because there's electric field from plus to minus. And also we have these coils here where current goes in one direction or the other, and according to the right hand rule there's going to be magnetic field in or out of the screen. And by combination of these two fields, one can direct the electron beam in any given direction here. Usually there's some kind of a screen here. For example, the old televisions used to work on this principle before the flat screens came to the market. Alright, exercise time. The question is, which of the following can experience a force when placed in the magnetic field of a magnet? A. An electric charge at rest. That is not true, because in order to magnetic force to have any effect on a charge, QVB, it has to have some velocity. So A doesn't work. Electric charge moving, yes. Electric current in a wire, yes. Electric current is movement of charge, so it's pretty much the same thing as this one. Also, another magnet would be experience a force, because you, as you remember, they have south and north poles, where the opposite poles are attracted to each other, and like poles will repel. In exercise F, we have a charge of unknown sign crossing initially the magnetic field diagonally. So it has velocity component parallel to the magnetic field and one that is perpendicular to it. The magnetic field doesn't affect the parallel component at all because F is Q times V cross B, and if V and B are aligned, their cross product is zero. So only change to the trajectory of this particle comes from the fact that the magnetic field couples with the perpendicular velocity component. And let's see how this works. So we'll use our right hand rule. So now we have only this perpendicular component. So if you take our right hand and point the fingers up to the direction of V perpendicular, and then we'll curl them towards B to the right, our thumb ends up pointing into the screen. So which means that the force for a positive particle would be into the screen. But if we follow this spiral closely, we see that when it's going up, it in fact starts to come towards the screen, which means that the force is in fact reverse of this, which only can mean one thing: the charge is negative. And how would you modify the drawing if the sign were reversed? So we would start from the same point, but it would start spiraling the other direction because the force now would indeed be towards the screen. So we would have trajectory something like this. So if in this case it's rotating clockwise, if you look from the left, the rotation would change to be counterclockwise. And it would still be propagating at the same velocity to the right because the magnetic field doesn't affect the parallel component of the velocity.